the rotation around this axis and the rotation around that axis will have the same effort, same moments of inertia. However, if I spear this thing in the middle and then rotate it that way, it's different. So this is called a symmetric top. We can have energy expressions for that we can work with a little bit. Then the third case would be, for example, something like water. This is going to be an exercise that you will do. You're going to have I'm going to represent it, I think I had it in the homework, as an XY2. I find that. So I'm going to do a problem with this, and then we'll see it. So if I have an XY2, you have the center of mass within here. The moments of inertia are different, no matter how you spin it. If I spin around this way, or flip it this way, or around the z-axis, all of the efforts are different. So that becomes what is known as an asymmetric top. And by convention, we'll compute these today. If you compute the moments of inertia, looking in the literature, you're going to have an IA, IB, and IC, where they're put in order from the largest then to the smallest. So here we have energies that would be like this. For the symmetric tops, there's actually introduced another quantum number. So here's the energy for a symmetric top. An asymmetric top are all different. So there's really no general expression that does that. But for a symmetric top, you've got this J times J plus 1 h bar squared over 2I. Then you have an IB, so that's the second largest. And then you have another term where you have another quantum number K. K has integer values going from minus J to plus J. Okay, so if J is 2, then K is negative 2, negative 1, 0, 1, 2, as we goes within there. So then you have the separation of these moments of inertia. Well, this is enough to get your foot in and to get some stuff done. And it comes into those cases. When these things, I think I have this here, yeah. If you look these things up, this constant h bar squared over 2I is in joules. So as it naturally would be. So if I have, this is the one for HCl. So I have h bar squared over 2I, I just produce a value for that. It comes out to be 2.12 times 10 to the minus 22nd joules. Rotational constants are not necessarily reported that way. They can be reported in a couple of different ways, or actually several different ways. If I take the joules divided by Planck's constant and the speed of light, joules divided by hc, keep this in mind, we'll need this later, gives you wave numbers. If I take joules and divide it by Planck's constant, which is joule seconds, I get hertz, reciprocal seconds, which I can then put into gigahertz, which is another common way it's represented. Later, when we do quantum statistics, we'll use rotational temperatures given as temperatures, where we have the joules divided by Boltzmann's constant, which is joules per Kelvin, so it gives a value in Kelvin. Now, one reference source that I cited that's very handy, but I also have it on the website, is go to the home page. You're going to see this CC database, CCC BD, whatever it is. So it's a National Institute of Standards database, and you can say, well, we'll have a molecule, and I can put something like water, so I put H2O, or I can type what I got H at O, so H2O. And when you submit that with all properties, it'll give you all sorts of interesting information. You've got the heat's formation, entropies, and so forth and so on. But it should give you, sometimes it crashed. Let me try it again. All right, here we go. But here are the rotational constants. It gives you a little bit of symmetry. But here are the rotational constants in wave numbers. If you click on this, it'll give it to you in gigahertz, however you choose. So here are the rotational constants for water, part of an exercise that you're going to do. So here is the product of the moment of inertia, is just kind of an added factor. They give you geometrical data. Here is the bond length between oxygen and hydrogen, 0.958, that's given in angstroms, and the bond angle, HOH bond angle, 104.4776. And then they have, there's more, there's atomic distances. There's all sorts of really interesting information that is presented for this, for any molecule that you choose. So it's a very good rotational source. All right, what I want to do then is say, how do we get those moments of inertia for a polyatomic molecule? Now, but this is then a rotation of an XY2. You're going to do this exercise for this molecule. If you're going to do it for H2S and SO2, I think it is, then you go to the database and check your numbers, okay, and see how they come out. So in this instance, the way a moment of inertia is computed is first, you have to find the center of mass of the molecule. Well, if I draw a dot here to be representative subtly, this is what the center of mass might be. If you have the mass times the distance and the molecule is rotating, the center of mass is where all that is zero. You have a homework problem that's just fairly easy to do, which I'll mention that as we're doing this. You've got a molecule A, B, and C. And I said, all right, let's say that the center of mass of the molecule was here. We call this distance S. Okay? So to find the location of that center of mass, what you do is you go, we'll call this, if I call this, what did I call it? RBC, I think. So I'll call it R2. So I call it R2, and I call this R1. So those are your bond distances. Okay? For this system, what you'll do is you say, all right, the mass of atom C multiplied by this distance here, which is R2 minus S. See, because it's R2, subtracting that S gives me the distance from here to here. Then I have minus, because I'm going in the other direction, the mass of B times S. And then finally, again, since I'm going in the negative direction, minus the mass of A, and I need this distance. Well, this is then R1 plus S. That has to equal 0. All right? So with that proviso, if we have it masses A, B, and C, you will solve this for S, and that will be the location of the center of mass from there. Okay? Once you know the location of the center of mass, then we can compute the moment of inertia around that center of the mass. So the moment of inertia then, whatever that S will be, it will be equal to the mass of C times this R2 minus S squared. So it's mass times the distance squared. Then I have plus the mass of B times S squared. So we essentially reproducing this, except your distances now are squared. And then plus the mass of A, R1 plus S squared. And that will give you then the moment of inertia.
Two questions. Why is the first equation equal to 0?
That's dynamics and physics. You know, if you have a true center of mass, then going in two different directions, the mass times the distances cancel out, they go to 0. It's just from classical physics.
Second question, why did the signs change in I? So we now have plus MBS squared?
Because these quantities are squared now, because now we're adding up all the masses that are around the center of rotation. So first we have to find the center of rotation, and then we produce I. Then I'll give you kind of intermediate equations to use. This is problem number 4. And then finally, when you're done with that, and kind of get I give you what the moment of inertia should look like. It's a relatively easy exercise. And then I give you the bond distances for hydrogen cyanide. So 1.064 angstroms and 1.156 angstroms. So you'll compute the moment of inertia for HCN, and then you can go back to that CCDBD database, look up HCN, and compare the answers that you get. So straightforward. So the other one, a little bit more difficult, is now this is an asymmetric top for you'll do like say H2S and SO2. So to kind of get you started, I'm going to do a little bit of a larger molecule, where I've got a molecule that I have as just X, Y, and Z with these angles, all right? So we're going to do this in general, and then we'll put some numbers in and see how this is done. to do this, once again, I need to find the center of mass. Well, the center of mass is here. I'm going to use the z-axis to find that, and using the same argument, I'm going to, and yours, we're going to have this z-axis here, and I'll mimic that. So this is going to be, you're going to have a bond angle, theta over 2, and this is your x, y distance, and you'll need that one as well. All right. So in here, for this particular system, I need to do the same thing. I need a mass times a distance, and add them all up and set them equal to 0. Well, for the first one, I have the mass of x, and I call this distance from the center of mass little x. So m of x times little x is going to be the mass times distance within here. Now I need to subtract from that because I'm going down. So it's going to be the mass of y, and I need this distance here from the center of mass to y. Well, that is xy minus x. So this will be xy minus x. All right, so that takes care of the rotation of y. And now the z, I need that vertical distance. Well, the vertical distance is from the center of mass here all the way down to here. So I will subtract 2, because I have 2 z's, 2 times the mass of z, and its distance is. Now this is, if you're given an angle here, some theta, then the half angle, of course, is theta over 2. The distance from y down to parallel in z is the yz cosine theta over 2. And then we have to add this distance here. So this is going to be then yz cosine theta over 2, then plus xy minus x. Okay, so that's the total distance from here down to that center of rotation, because we're looking at it as a rotation here. Well, that then is set equal to 0. You know, we solve for x. Now it's just an algebraic exercise, and when you do that, you come up, so here's the result. Here's the mass of x and everything I've kind of put in place. Set that equals 0, just do a little bit of algebra, and you get x as being this value. Now it's very common when you find a center of mass that the denominator has just some masses. It's very common. So there it is. Once you have that x, now we're ready to rock and roll. We can find out that what things that we need. Now yours here, your center of mass is going to be somewhere in here. By the way, if depending on the weights of these items, it could be possible that where I put my dot is in the wrong place. Let's say the center of mass, let's say z's were very, very heavy, for example, the center of mass might be down here. If you did that, this is still correct. You get exactly the right answer. The only thing that will come into play is that the x, as I defined it, would be negative. Okay? So, which is okay. It still works. It's still exactly right, no matter where you place your dot. In here, clearly we're going to have a dot somewhere here.
How do you know where to guess to put the dot?
And that's my point. It doesn't matter. It doesn't, no matter where you just start, and what I called, like if I put my dot here, and I call this distance x, and that distance would be xy plus x, I'll still get the right answer. In that case, if I defined it that way, it would be positive here because I defined my x as in the vertical axis. If the center of mass were actually down here and I define my x up here, I would get a negative value. But it still works. Even if it's negative, you'll still get exactly the right answer. So don't let that upset you if you see that. Okay. All right. So now that we know where the center of mass is, we can now begin to rotate. Now this molecule, as I produce it, is symmetric. So since it's symmetric, I do know that the center of rotation is along that axis. If Z and this Z, if they were different, this was chlorine and hydrogen or something along that line, well, that center of mass would be shifted over. something like that. I've given you a symmetrical molecule here, that if this were X, Y, Z, then your center of mass might be somewhere here. And, which is okay, you still, but you would have to now work a little harder to find the center of mass in both the X and the Y direction of the plane. Right? But since I'm amazing, I just gave you nothing but symmetrical molecules to work with to make our life a little bit easier.
Should we expect a non-symmetrical one?
What do you expect?
Would you be
I didn't have it planned. I don't think I planned to do that. So, actually, it gets a tad laborious, which is kind of beyond the point of which I'm at. So I don't think I'll do that. If I do that, you can get it. All right.
Okay, everything's.
Have you heard that? It's being recorded here too. So, you got it on recording? All right. I will hold to that. All right, so we have our X values down. Let's find the rotation around the vertical axis. Okay? This one is the easiest one. So I'll call it IZ, because we're rotation around the Z axis. It's typically, X, Y, Z, but that's the way I've labeled it, we'll call that. Well here, if it's rotating along this axis, these are not part of it. They're in the center of rotation, so it costs no energy to twist them around, you're just spinning them. So these are the only ones that matter, so we need that distance. We need the distance from the center of the rotation, which is from here to here, which is YZ times the sine of theta over 2. So the moment of inertia in the Z-axis is easy. It's 2, since I have 2 of them, times the mass Z times the sine of the bond angle divided by 2. That's it, we're done. Easily done, okay? So now we need another, let's do another one here. And let's do then this one here. Okay? So let's do that rotation there. I'll call that X or Y. I forgot what I call it, which one I call it. Typically, I go X, Y, and Z. So I call this, typically Y, but we'll call it that. We'll see what, I don't remember what I did on the X. All right, so for there, the I in Y is going to be, we need this distance here, because this is going to be rotating around. That distance is X. So it's going to be mass of particle X times X squared. Mass times the distance squared, that's your moment of inertia. Now I will add to that, all moments add, because it's a rotation. I need this distance here and the mass of Y. So it becomes then the mass of Y times the distance from the center of the rotation, which is X, Y minus X. And once again, squared. So that'll be the moment of inertia around the Y-axis. For yours, you do the very same thing. So you're gonna have, here's your rotation. Here, first off, this is obviously going to be your bond distance X, Y times the sine of theta over 2. So for rotation around that Z, you'll do the same thing I did here, straightforward. For your Y, you're gonna need this distance here, and you're gonna need that distance there. You need twice. Because this is that's the center of rotation, so Y is moving around the axis. Even though it's bonded at an angle, it's moving around the axis at this distance. Well, that's the same thing we need to do here. I need this distance here, because Z is rotating around that axis. So that distance is, I have this YZ cosine theta from here to here, and I have this, what I call this XY minus X as the distance from here to here. So from here down to the Z, same as we had done before, this is going to be plus twice the mass of Z, and it's going to be then XY minus X plus YZ times the cosine of theta over 2 squared. And that would be then the moment of inertia in that direction. Okay? Now the tricky one. Not too bad, really. So now we're going to do this axis here. In this axis, x is rotating around, and that's the distance x here. The y is that distance there. We can do that one. So let's do that one. So I'll call that I of x. And so yours is going to be that distance there. So I of x is going to be the mass of x, cap x, times x squared. That accounts for the rotation of this all the way around here. The y, then it's going to be that one as well, the mass of y times x y minus x squared. Okay? Now the tricky one. To get the rotation of the z around the center of mass here, I need the distance from here to here. In a rare feat, I'm going to use actually colored chalk. So I need that distance there. All right? That can be obtained in one of two ways. You can either do just kind of Pythagorean theorem. You know the distance from here to here, and the distance from here to here. So that squared plus that squared, square root will give you that distance there. Or you have a distance here, and then this distance here, and these are two vectors, and you can use the law of cosines to get that. And I've done them both. So for here, if I use the Pythagorean theorem, I call that dp, there's the distance then here. So there's a yz sine angle over 2 squared. And there is the distance from the center to the bottom, as we had done before, squared, square root, and that gives me 1. If I use the law of cosines, I need this distance here, xy minus x squared, and then this length here, which is simply yz squared, and then minus 2, xy minus x, yz, and then the cosine, and because of the way that angle is operated, it's pi minus pi. Either one will work. So, but you're going to need for yours the distance from here to here. So that I will do twice. So we then produce that one. So we produce that distance. I'm just going to call that 2. I just have two z particles. So 2 times the mass of c, and I'll just use my dp squared once I calculate it, right? Or whatever that result may be. So then when you finalize all those things, here they are. So that was the good. I didn't label them right. So here's my x, my y, and my z. Or so here is using either the Pythagorean theorem or the law of cosines. Either way, get you the correct answer. So let's apply this now. So I used SOH2. So I need then bond angles and bond lengths. So I set the XY, my oxygen and sulfur, as 1.43 angstroms, my SH at 1.34 angstroms, and I set that at 120 degrees. And I put it times pi over 180 to make it in radians. If I just put it in 120, it would have done that. Anyway, so then I need all the masses. I have sulfur as my X. Is that what I had? I think I inverted this. So I have my X as my sulfur, my Y is my oxygen, so I should flip those over. So that's massive. Let me make that massive Y. I just mislabeled. X, and then of course we'll have the hydrogens all within there. So here I just copied and pasted everything from above. So once we have solved for the center of mass, it comes out to be about 1 angstrom. Yeah, I was kind of curious. Worked out just very nicely, didn't it? And then here's my D's. So I have the distance again from here to here. Using the law of cosines, I get 1.599 angstroms, and using the Pythagorean theorem, I get the same answer, 1.599 angstroms. So once I have those in place, I got all my moments of inertia in place, I can then compute them. So I just put the equations in that we produced. So I have a 4.497, 4.508, 4.046. They are all different. So that demonstrates that it is indeed an asymmetrical top. And you will come out with that as well. So then I can now compute the rotational constants, and then I can look them up and compare them. So I have like the A, B, and C that I listed, I just called them in that. Here's my H bar, 4 pi I Y, I Z, I X. And if I put it in gigahertz, there they are there. If I put it in wave numbers, there they are there. All I need to now is just go to the databases and look it up. And also I put it in temperatures as well. So if I take the constant H bar squared over 2I divided by the Boltzmann's constant, I get constant in what's called rotational temperatures. And like I said, we will see that forward. So that is for that type of a top, and you'll do one almost identical for H2S and SO2. You'll look up the databases and see how close you are. I also produced, now this is for homework number 6, problem number 6. I'll go ahead and talk about this. This is a molecule that would be representatives like of ammonia. So you've got now, what is it, the C3V symmetry on there. And in fact, the homework problem, I gave you then the moments of inertia for ammonia. So actually, let me think if you actually need to. So for the moments of inertia of ammonia, which is a symmetrical top, going back to the rigid rotor problem, you'll be using this right here. And I say, I've given you the moments of inertia, IB and IC, and IA. Notice that the IB and C are identical. IA is different, so that makes it a symmetric top. So I want you to compute the rotational energy states for J equals 0, 1, and 2 with all allowed values of K. So you'll have J equals 0, of course K will be 0, that will be an energy 0. Then you'll have J equal 1, then you'll have K of -1, 0, and 1. You'll have 3 states there. And then J equal 2, you'll have that, so K will be -2, -1, 0, 1, and 2. So you'll have then individual states that come into there. And then I say, so let's suppose that we promote the ammonia molecule from the J0, K0 to the J1, K1, let's say spectroscopically. What would be the wave number of light that we would be required to do to excite that molecule to that next state? So again, this you'll just do you'll calculate this for the particular states given. So you'll have E11 minus the E00 converted into wave numbers, and you'll have it from there. And then I say compute the moments of inertia for the ND3, where D is now deuterium. That's where you can use this worksheet. So go back to the C3V worksheet that I provided for you. This does all the development just like we did for this system here. So I have the worksheet here. On this, I have several different molecules. The green is ammonia. The red is chloromethane. Notice chloromethane is still a symmetric top, right? Because even though it's tetrahedral, methane is a spherical top. Let me show that one. And then finally, I got blue and carbon tetrachloride. So let me, to transform any of these, let me go first to the ammonia. So the ammonia, here are the 2 moments of inertia that are produced within here. Let me just change the ammonia to the yellow, the methane. So to that, I'll just kind of bring these down into here. So there's the methane. And if you look at the moments of inertia, they're now identical. Spherical top comes into play there. Put those back in play. But what you'll do for the homework is simply change these masses here from hydrogen, change it to deuterium. Okay? And you'll be able to produce the moments of inertia then for ND3. So it's just simply using that worksheet to produce your number for you. So it'll save you a lot of time. So that is the moments of inertia for ND3, the deuterium. And then also recompute the wavelengths of excitation for the ND3. So you'll do exactly what you did for NH3, do it for ND3, and see, could you distinguish that in a spectrum? Could you identify the deuterium isotope from the hydrogen version of it? And then just a hypothetical question, what would happen if the molecule were now NH2D? Could we use this? Well, now we're all over the place. If I have an NH2 with a D, now your center of mass is not in the middle of the molecule, it is now shifted over. Same argument I made here. If this were X, Y, Z, and they were different, your center of mass is going to be probably shifted to the left or right. So this symmetric top thing would be go completely out the
It would be
window.
arranged that way, that if it was NH2D, wouldn't it be arranged this way?
If they're NH2D,
Like NH2D?
because the NH2D is not planar, that could get you the problem. It's trigonal pyramidal. So that wipes that one out as well. So every molecule has its symmetry, and every molecule has attacks that go on to that. Of course, now computers will do this, obviously, doing that very soon. So that'll number 6 is an easy one to do, even though it's not due till 5 days from now, something along that line. But number 4 is straightforward. That's not too difficult. Then number 5. Once you get this going, number 5 is you produce those numbers. Go to the database. You can find it.
So number 4 and 5 are too low?
Yeah. Then we have 6 on Wednesday.
Okay.
Yeah. According to the schedule, but I thought since we're on that topic, I go ahead and address 6. You're welcome to do it during the day. All right. So polyatomics, diatomics, everything in place. We've got our energies, we've got location. We're going to place these things later. We have now 5 quantum numbers. 3 of them associated with translational motion, and NX, NY, and NZ. We have 2 more associated with rotation, J and M. We got 1 more left. Of course, we have 1 more motion left, and that is vibration. So I would just introduce it, and then we will then attack it quantum mechanically later. So in the harmonic oscillator, this is called the harmonic system, well, we'll see, does that really apply? We need to ask that particular question. But if I were to write then the Newton's equations of motion, well, first off, we're going to have a potential that is 1/2. Now remember, we've got a molecule, or an atom, and an atom. And what we're going to do is we're going to say is attached by a spring, a Hooke's law spring. The potential of Hooke's law is 1/2 K, where K is called the force constant. The force constant will determine its frequency, because if it's a very, very, very stiff spring, such as, let's say, nitrogen gas, K is going to be a larger number. If it is a very loose spring, like chlorine gas or something like that, K is going to be a smaller number, and that will determine its frequencies of vibration. But the Hooke's law says I need the distance from particle 1 minus the distance from particle 2, so there's your distance here, and we're going to be looking at the deviation from equilibrium, which is minus RE squared. To apply Newton's equations of motion in this, we run into an immediate difficulty, because we have the mass times the acceleration. So I have mass particle 1, d21 dt squared. The mass of particle 2 times its acceleration, d2x2 dt squared. Then the derivative of the potential energy, the negative of that, which is then the force, which is the force constant. Now I have this x2 minus x1 minus xe, or I call it equilibrium bond distance, or I call it RE up here. And this is then the Newton's equation of motion. We run into an immediate problem, is that it is coupled together. So I can't separate the motions of 1 and 2 in doing this. Well, the solution to solving this is the same solution that we adapted for the rotational to get away from center of mass motion. We're going to use the center of mass coordinate system. So not reiterating, not deriving, we've already seen it several times now. So I'll define an x relative, which is the distance between the two. Here's the x center of mass, mass 1, x1, m2, f2, over the total mass, so forth. And now the potential energy becomes just x relative minus RE squared. Greatly simplified. Now, when this is broken apart, just like we have done a couple of times, you end up with 2 differential equations. One involving only the center of mass motion, That's the particle in the box problem. We're done, we have this solved. Have done it, we can go move on. But now you have the relative motion. You have, remember that the mass, this is the sum of the masses. Here is your reduced mass again. And this is going to be the acceleration of xr dt squared. Now your force constant, xr minus re, it is now uncoupled. I have one coordinate to deal with. For convenience, and I mentioned this, I had you solve this differential equation in homework for this reason. So when we arrive here, you'll be a little bit more familiar with what's happening. What I had you do in the homework is we just had something like, and I use, what did I use here as my value x? So I just called, I use the value x as being xr minus re, or equilibrium bond distance. The reason I do this is because dx is equal to dxr, and so everything transforms completely. So what I can do is I can just call this x, call this x, then I have a simple differential equation that we can solve just like we've solved many times. So doing so, I have a mu d2 now just plain x. I should probably change that to z just for clarity. Plus k x is equal to 0. This is a familiar differential equation, rearranging d2x dt squared plus k over mu x is equal to 0. I will call this omega squared, okay? And from that, that is one of the same differential equations that we've solved many times. We can write the answer to that immediately, because that is the positive sign here, second order differential. So I can write immediately that x is a times of omega t plus b times the sine of omega t. Okay? Note, omega is, of course, the square root of k over mu. This has units of radians per second. Radians per second. We would like to turn that into a frequency of cycles per second. So since there are 2 pi radians per cycle, if I convert this, the frequency now in reciprocal seconds and cycles per second is going to be mu divided by 2 pi, or 1 over 2 pi root k over mu. And we'll be using that several times. Turns out the quantum result is identical. So there is then the frequency in cycles per second, where omega is radians per second. Well, here's our general differential equation. We have 2, of course, undetermined coefficients, a and b. We need to apply some initial conditions. So the one I have chosen is that, okay, I'm going to take my molecule, my spring, I'm going to stretch the spring out to some amplitude, I'll call it A0, and it'll be initially at rest. Okay? So I will have x at 0 is equal to, I'll call A0, and that's what we will call the amplitude. And I will say that dx dt at 0 is equal to 0. So I'm stretching it, and it is at rest. And when I start the clock, I let it go. Right? So to do this, if I set 0 in for t for all these, that whole thing goes to 0. Putting 0 in for t here gives cosine of 1, becomes at 1, so x becomes a. So from that, we can deduce that a is then a naught, or what I call the amplitude. For the other one, dx dt is minus now a0 sine omega t plus now, it's actually just a minus omega, plus an omega b cosine omega t. And again, at t equals 0, this is the velocity is 0, it's not moving. If I put a 0 in for t here, that whole thing goes to 0. If I put a 0 in for that t, that becomes omega b. So from that, I deduce that b is equal to 0. So just boundary conditions like we've applied 100 times. So there it is. I've got A0, B0, or plot the thing, and there it is. There's no real surprise here. Starts out, I set the amplitude at 1 just for convenience. So it starts off at an amplitude, again, it starts oscillating back and forth, just exactly as you would expect. So then you have your, of course, your frequency, as I mentioned, is the angular over 1/2 pi root k over mu. It is interesting to note, remember when we were doing heat capacities? For heat capacities, every direction in translational motion contributed a 1/2 r. So we had 3/2 r for translational motion. Every rotation contributed 1/2 r. But then we had this term. We had this like 3n minus 6 r for vibration. Well, this, it has 1/2 for translation, 1/2 for rotation, but a full r for every vibration. Here's why, because there's two energy components involved. There is a kinetic energy part and a potential energy part. Because you have those two parts of the energy, you get a full R out of the deal. Just kind of a little side note on that. If I take the kinetic and potential energy and add it together from our result, it's interesting to note that the total energy is 1/2 k A0 squared. It is independent of time. So what we've got is originally stretched out, high potential energy, no kinetic energy. At its equilibrium point, it's screaming towards the middle. So it has all kinetic energy, no potential energy, and it just goes back and forth. And so, but when they're added together, the entire energy is conserved. Well, then the last question, before we see what the quantum results do on Monday, I want to know where the particle is to be found. Do you have an intuitive thought of what the probabilities might look like for a particle? Where is this going to spend most of its time?
In the middle.
Okay. Any other guys?
0.
You think the middle, or what?
0.
You think it's 0? Okay. Think of it this way. Let's look at, for example, a pendulum, which is essentially the same thing, right? You have a pendulum. Pendulum is screaming through the middle. Remember, the clock is constant. So how much time does it spend in the middle when it's going rapidly through it? Not a lot of time. Then it slows down, comes to a stop, but the clock is still ticking, right? So it spends a lot of time turning around and then accelerating again, and then when it hits the equilibrium point or 0, it's going fast again. So it's going to probably spend more time on the ends. Well, I played the same game we did with the particle in the box. I wanted to just find